If you were to take any everyday object, say a coffee cup, and break it in half, then in half again, and keep carrying on, where would you end up? Could you keep going forever? Or would you find a set of indivisible building blocks out of which everything is made? Today, me and my friends are going to explain more about the standard model and beyond. Before we start, let me introduce myself. Hi, my name is Muhammad Aliff bin Azisham and my matrix number is 200575. Physicists have found the latter. The matter is made out of fundamental particles, the smallest things in the universe. Particles interact with each other according to a theory called the Standard Model. The Standard Model is a remarkably elegant encapsulation of the strange quantum world of indivisible, infinitely small particles. It also covers the forces of govern how particles move, interact, and bind together to give shape to the world around us. So, how does it work? Zooming in on the fragments of the cup, we can see molecules made out of atoms bound up together. A molecule is the smallest unit of any chemical compound. An atom is the smallest unit of any element in the periodic table. But the atom is not the smallest unit of matter. Experiments have found that each atom has a tiny, dense nucleus surrounded by a cloud of even tinier electrons. The electron is, as far as we know, one of the fundamental, indivisible building blocks of the universe. It was the first standard model particle ever discovered. Electrons are bound to an atom's nucleus by electromagnetism. They attract each other by exchanging particles called photons, which are quanta of light that carry the electromagnetic force, one of the fundamental forces of the Standard Model. The nucleus has more secrets to reveal, as it contains protons and neutrons, though once thought to be the fundamental particles of their own. In 1968, physicists found that protons and neutrons are actually made of quarks, which are indivisible. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up. The nucleus is held together by the strong force, another fundamental force in the Standard Model. Just as photons carry the electromagnetic force, the particles called gluons carry the strong force. Electrons, together with up and down quarks, seem to be all we need to build atoms and therefore describe normal matter. However, high energy experiments reveal that there are actually 6 quarks: up, down, strange, charm, bottom, and top. And they come in a wide range of masses. The same was found for electrons, which have heavier siblings called the muon and the tau. Why are there only 3 different versions of these particles? This remains a mystery. These heavy particles are only produced for very brief moments in high energy collisions and are not seen in everyday life. This is because they decay very quickly into the lighter particles. Such decays involve the exchange of force-carrying particles called the W and Z, which, unlike the photon, have mass. They carry the weak force and the final force of the Standard Model. This same force allows protons and neutrons to transform into each other, a vital part of the fusion interactions that drive the sun. To observe the W and Z directly, we needed the high energy collision provided by particle accelerators. There's another kind of Standard Model particle called neutrinos. These only interact with other particles through the weak force. Trillions of neutrinos, many generated by the sun, fly through us every second. Measurements of weak interactions found that there are different kinds of neutrinos associated with the electron, muon, and tau. All these particles also have antimatter versions, which have the opposite charge but are otherwise identical. Matter and antimatter particles are produced in pairs of high energy collisions, and they annihilate each other when they meet. The final particle of the Standard Model is the Higgs boson, a quantum ripple in the background energy field of the universe. Interacting with this field is how all the fundamental matter particles acquire mass. According to the Standard Model, the ATLAS experiment on the Large Hadron Collider is studying the Standard Model in depth. By taking precise measurements of the particles and the forces that make up of the universe, physicists can look for answers to mysteries not explained by the Standard Model. For example, how does gravity fit in? What is the relationship between force carriers and matter particles? How can we describe dark matter, which makes up most of the mass in the universe but remains unaccounted for? While the Standard Model provides beautiful explanation for the world around us, there is still a universe worth of mysteries left to explore.
Hello everyone, my name is Muhammad Zikri bin Zakaria and my metric number is 203576. For my part, I am going to present about the characteristic and properties of the Standard Model and beyond. First, let's look at the Standard Model. So, the Standard Model consists of quarks and leptons which act as mediators for the interactions produced from the four fundamental forces of nature and the Higgs boson. Among these particles, Higgs boson is considered relatively new discovered particle. Hence, let's move on to see more about Higgs boson in Higgs field. To let the Standard Model of leptons and quarks be mathematically consistent, British physicist Peter Higgs showed that a field named Higgs field must exist everywhere in space. The particles gain their characteristic masses when they interact with the Higgs field. The stronger the interaction between the particles and Higgs field, the greater the particle's mass. The mediator of the Higgs field is known as the Higgs boson, while the mass of the Higgs boson cannot be estimated from the Standard Model. It was thought to be substantial and is very large when compared to proton. In 2012, the first Higgs boson were detected in collision between protons that took place inside the Large Hadron Collider (LHC) at European Organization for Nuclear Research. This suggests that the Higgs field concept is correct indeed. Current experiments showed that the mass of Higgs boson is around 125 giga-electronvolt per c², which is larger than the masses of positive and negative W and neutral Z bosons. A grand unified theory (GUT) is a model in particle physics in which, at high energies, the three gauge interactions of the Standard Model comprising the electromagnetic, weak and strong forces are merged into a single force and so are well beyond the reach of any foreseen particle collider experiments. This theory was given by Pakistani scientist Abdul Salam, who shared the Nobel Prize with Weinberg and Glashow in 1979. Grand unification theory, or GUT, is a model that tries to describe the universe by saying that it can combine three of the four fundamental forces into one single equation. These are three of the fundamental four forces of nature which are responsible for all the pushes and pulls in the universe. The four forces are the strong nuclear force, the weak nuclear force, the electromagnetic force, and the gravitational force. Although this unified force has not been directly observed, the many GUT models theorize its existence. If unification of these three interactions is possible, it raises the possibility that there was a grand unification in the very early universe in which these three fundamental interactions were not yet distinct. There is currently no hard evidence that nature is described by a grand unified theory. One of the few possible experimental test of certain duty is proton decay and fermion masses.
Hi, Assalamualaikum, and good evening. So, my name is Aidid for the law bin al my metric number is 2000797. As for today, I will talk about the applications of particle physics. So, in general, do you know that MRI use the application of particle physics? The cargo, what about cargo? How does it use the particle physics? Diapers and nuclear. Okay, so then let's proceed. In medical MRI is magnetic resonance imaging. Particle accelerators and detectors was first developed for particle physics are now used by every major medical center in the nation to treat and diagnose millions of patients. So the function of particle physics is the first developed are now applied in MRI to give a detailed image of our bodies, distinguish gray matters from white matters in our brain, distinguish cancerous tissues from non-cancerous tissues, reveal blood flow and sign strokes. So that is in terms of medical. And for the next one, industry and safety. So this is about the cargo before I said. Cargo scanning. Cargo scanning is we know that port is used for industry and it is also need to be safe. So cargo scanning also apply the particle physics, which use high energy X-ray generated by particle accelerator to identify the items and keep the port safe. So if there is any suspicious item, the particle accelerators can that produce the high energy X-ray can detect that if there's any suspicious item or dangerous thing inside the cargo. So the result cargo could give us the screeners, means the person who read the X-ray generated. They could see a more detail about the nature of the cargo, means they could identify the item more detail without opening it. Next one, okay, for lifestyle, I'm using diapers because diapers nowadays are used in all kind of human, despite the gender, the age. So, using a particle accelerator, the scientists were able for the first time to see the detailed wet structure of the superabsorbent polymer material used in diapers. Okay. They can improve the superabsorbent polymers by adjust the formula until they had a great material. As for the applications, the particle accelerators scan the polymer. So the polymer which has the best absorber will be applied in the diapers this day. So that's how the particle physics apply to scan the perfect polymer for the superabsorbent. Okay. This is the growing legs. The science and technology of particle physics has contributed to many other areas, benefiting the nation's well-being. Simulation of cancer treatments, reliability testing of nuclear weapons, curing of epoxies and plastics, improved sound quality in archival recordings are just few examples on a growing list of practical applications. Okay, that's all for me. I did. Thank you.